Hello, students, and welcome to the 45th lecture on particle physics. And on the last turn, we were discussing about lepton quark symmetry. What I had told you that the interaction strength of a particular flavor of a lepton with its own generation of lepton, like nu e with e minus, or e minus with nu e, or nu e bar with E plus, and incoming nu E bar and outgoing E plus, which is emitting a W minus. This is of the same strength GW, and then this is true for quarks or not. That is what is the debate. And what I had told you, that initially it was thought that if we have a nu E and electron as the first generation of leptons which are participating in the weak interaction processes, we have U and D as the doublet which is participating in the weak interaction. Now, the coupling strength when U is emitting a W plus and changing to D, or U bar is emitting a W minus and changing to d bar, because u bar charge is minus 2 by third and d bar charge is plus 1 by third. This can happen if it emits a W minus, and this should be in general of strength GUD at the vortex. But if lepton quark symmetry holds good, then GUD must be equal to GW. But what we discussed on the last turn, that besides the pion decay, which involves quarks of the same generation, we have also kaon decay, which we have observed, where a k plus is giving rise to a mu plus and a nu mu, or a k minus is giving rise to mu minus and nu mu bar. Or not only this is true for k plus or k minus, we have also lambda decay or sigma minus decay, which is only possible when a S is changing to U, or if you take antiparticle of that, U is S bar is changing to U bar, etc. Therefore, now here there is involvement of first generation quark U and D with the strange quark, and that is what was the point of discussion on the last turn. The important thing then is that the strange particle decays are suppressed as compared to the decays of non-strange particles. This is what I am talking about, the experimental observation, that the decay rate for K plus decaying into mu plus nu mu upon the decay rate pi plus decaying into mu plus nu mu, or the decay rate of K minus decaying into mu minus nu mu bar, or the decay rate of pi minus decaying into mu minus nu mu bar. This is not of the same rate. Here you have a conversion of or involvement of quarks of the same generation. Here you have involvement of U with strange. Here you have involvement of U with strange, where here you have the involvement of U with the same generation of the quark. So what was observed, that if you have the involvement of U with S, then that decay rate is suppressed as compared to where you have the involvement of U with D, or vice versa. So for example, K plus nu mu is suppressed by a factor of 1 by 5 as compared to pi plus decaying into mu plus nu mu. And similarly, this is true for K minus decaying into mu minus nu mu bar, and pi minus, that is decaying into mu minus and nu mu bar. Then the strange particle decay follows delta S is equal to 1 and delta S is equal to delta Q rule, where delta Q and delta S are respectively the changes in hadronic charge and strangeness. Now let me spend a few minutes on this. For example, if I am talking about a neutron decay, a neutron is decaying into a proton plus electron plus antineutrino, and a lambda is decaying into proton plus electron plus antineutrino. And here a pion is decaying into mu minus and mu bar. And here K minus is decaying into mu minus and mu bar. Then what we are talking about? We are changes in the hadron charge and strangeness. Okay, therefore we talk about S and Q. Strangeness here is 0. Pions are non-strange particle. Charge is -1. Therefore delta S is 0. Delta Q is +1. Final minus initial. If we talk here, S is K minus -1. Q is -1. Here there is no strange quark. There is no hadron. Therefore delta S here is +1 and delta S here is also, delta Q here is +1. If we talk about a neutron decay, then strangeness and charge. Strangeness is 0. For proton it is also 0. For Q, here charge is 0 and proton charge is +1. Therefore delta Q is +1 and delta S is 0. Here strangeness and charge. S is -1. Charge is, strangeness for proton is 0. Charge is 0 and here for proton charge is +1. See, mind it, we are only taking hadrons into account. Otherwise, we have to conserve charge. That is, that belongs to the category of exact conservation laws. No way we can violate them. Therefore, delta S final minus initial is +1 here and here also final minus initial +1. Therefore, what we are observing is that delta S is +1, delta Q is +1, delta S is +1, delta Q is +1. That is what here we are mentioning delta S, delta Q rule. Delta S, delta Q rule. And here what is happening? Delta S is 0 and delta Q is +1. Delta S is 0 because it is involving no strange particle. Here also in this case it is involving no strange particle. Similarly, therefore the important point is that if we have delta S is 0, delta Q is +1 or -1, because I have taken final minus initial, you could take initial minus final. That is why this is +-1. And then when we have one case where delta S, delta Q is +-1. Therefore, what was found that if we are having delta S is equal to 0 and delta Q +-1, then the decay rate for such processes are dominant than where you have delta S equal to delta Q equal to +-1. And that is why the decay rate for K plus or K minus or lambda or sigma decaying into non-strange quarks, their decay rates are suppressed. And what was found that if you have a delta S is equal to delta Q is equal to +-1, these decay rates are suppressed. While if you have delta S is equal to 0, delta Q +-1, then they are more favored. Mind it, just I am telling you that if delta S is equal to delta Q is equal to +-1, they are suppressed decay rates or processes. Then where we have delta S is equal to 0 and delta Q +-1. And let me take another example. If I am talking about sigma plus decay into neutron plus E plus nu E, then you see strangeness -1, this is 0, charge +1, this is 0. Therefore, here delta S is +1, final minus initial, and delta Q is -1. And such decays have never been observed. They are called forbidden decays. And if you notice that delta S is equal to plus 1, and delta Q is minus 1, that means simply that if we have delta S is equal to minus delta Q is equal to 1, or delta S is equal to minus delta Q is minus 1, that this can be, since we took final minus initial, you can take initial minus final, then delta S is minus 1 and delta Q is plus 1. That is why I wrote both the cases, that if you have delta S is equal to minus delta Q equal to 1, or delta S, see here the sign is important. Here if I am not writing any sign, that means that stands for plus sign, and here this is minus sign. If these are the cases, then those processes are forbidden processes. At the quark level, you can understand it by looking at the quark composition. What is the quark composition of sigma plus? It is straightness minus 1 particle, but at the same time its charge should be plus 1. This is a baryon, therefore there should be 3 quarks, and that is why the quark configuration for this is UUS, while here this is UDD. Therefore what you are seeing, that in the initial cases of pi minus or k minus or lambda or sigma minus that we talked about, we had strange quark changing to U quark, or U quark changing to strange quark, U quark changing to D quark, or U quark changing to strange quark, and there was only one change. Here you can see that proton is changing to neutron by when a U quark is changing to D quark, or neutron is changing to proton when D quark is changing to U quark. A lambda is changing to proton when a strange quark is changing to U quark. A sigma minus is changing to neutron when a strange quark is changing to U quark. Therefore, mind it, here we are talking about the one change in the quark from strange to U up quark, or up quark to strange quark, or anti-up to anti-strange, or anti-strange to anti-up. But if you have the involvement of two quarks where you need to change their flavors, those will be the forbidden processes. And mind it, how we can understand it? In simple language, we can understand, though I will again come back to this, but for the completeness to convince you, I am writing the fact that you see, when we are talking about a change of neutron to proton, electron and anti-neutrino, I am talking about an exchange of W minus or exchange of W plus. Now if we have, and this I told you, Feynman rules tells us that at the matrix element you have 1 over mw square, and since the decay rate or the matrix element or the cross section involves matrix element square, therefore for the matrix element square you have the square of this, that means 1 over mw to the power 4. Therefore the important point is, at the matrix element you have 1 over mw square. When you are talking about matrix element square for the decay rate or the cross section from the Fermi's golden rule that has been taught to you, then this is matrix element square, and that fellow is 1 over mw to the power 4. Now you are required to convert two quarks into different flavors, and that means you need 2 W bosons, and that means you need 1 over mw to the power 4 at the matrix element level, and 1 over sorry, 1 over mw put to the power 4 for the one in the matrix element square, and for the another exchange 1 over mw to the power 4. That means in total 1 over mw to the power 8. And then you have the weak coupling, which you have seen that is again extremely small. Therefore, this is 1 over 80 to the power 8. Roughly, you can say that 1 over 100 to the power 8. And that is really a very small number. And that is why any change for two quarks flavor, those will be completely forbidden processes. And that is why if I talk about, for example, let me just, before moving ahead, let me just talk about an omega minus decay. Then you know from phase space consideration, an omega minus should decay into n plus pi minus, because neutron is the lightest possible baryonic particle with proton. If you assume the proton and neutron mass to be almost the same, though neutron is 1.3 MeV heavier than proton, this has never been observed. Why? Because this is d du and this is u bar d, and here all of them are strange quarks. Therefore, all three have to get converted into non-strange quark, and that means you need for 3 strange quark one more fellow 1 over mw square. That means 1 over mw to the power 6 at the matrix element level, and then at the matrix element square level 1 over mw to the power 12, and that means 1 over almost 100 to the power 12, and that is, you can see that it will be a very, very small number. And that is why we don't observe this process. But without going into all the details about it, directly we can say that straightness is minus 3, this is 0, this is 0. That means this is delta S final minus initial. We are conserving charge, but the strangeness number that is changing is by 3 unit, and this will be forbidden process. Not only this, let us take another example. Sigma 0 plus pi minus or lambda 0 plus pi minus. This sigma 0 is UDS, lambda 0 is UDS, this is U bar D. Now here what you see, that you have to convert two strange quarks to two non-strange quarks, because with sigma 0 and lambda 0 you have still one strange quark living with you. Therefore, then again the same analogy, you can see that matrix element square will be proportional to 1 over 100 to the power 8, and that will be a forbidden process. But instead of that, if I write cascade 0 pi minus and omega minus decaying into cascade 0 and pi minus, you see straightness minus 3, here straightness minus 2, this is 0, charge minus 1, I'm sorry, charge minus 1, this is 0, this is minus 1. Therefore, the change in strangeness final minus initial is by 1 unit, and change in charge minus and minus of minus 1, that is 0. Therefore, you see that change in strangeness is by 1 unit, or instead of omega minus, you can also talk about cascade minus plus pi 0. Here, strangeness is minus 3, this is minus 2, this is 0. Charge minus 1, minus 1, 0. Therefore, here delta S is plus 1 and delta Q 0. Therefore, these two are the dominant decay mode of omega minus. And that means you have the only conversion of one s quark to u quark. And that is why I am writing here the strange particle decays follow the delta S is equal to 1 and delta S is equal to Q rule, where delta Q and delta S are respectively the changes in hadronic charge and strangeness. Therefore, remember it that if delta S is greater than or equal to 2, that those processes will be forbidden processes. Delta S, let me write it clearly, that delta S greater than equal to 2 will be forbidden processes. And then the other thing that I am telling you, that if delta S is minus delta Q, that is equal to plus minus 1, that will also be forbidden process. But if delta S is equal to delta Q is equal to plus 1, or delta S is equal to delta Q is equal to minus 1, that will be suppressed, but those are observed in nature, like K minus decay, like lambda decay, like sigma decay, but they are suppressed in comparison to, say, for example, when you compare neutron decay versus lambda decay, or when you compare pion decay versus kaon decay. And this one should keep in mind always. The other important point is that when you have the involvement of strange particles, then, for example, strangeness changing decays in which delta is Q is equal to 0, like KL0 is decaying into mu plus mu minus. While you see in the experiments, you observe the processes like K plus decaying into mu plus nu mu, or you observe the processes like K minus decaying into mu minus and nu mu bar. But here what I am telling you, that you have a neutral kaon, long-lived neutral kaon, that is decaying into mu plus mu minus, or a K plus minus decaying into this mode or this mode. I have written all those modes, and they are highly suppressed. These modes are highly suppressed and they have not been observed. This was true also in 1950s, that nobody observed such type of processes in the experiments. Therefore, the important point is that strangeness changing delta is equal to 1 currents follow delta is equal to I half rule, in contrast to the delta S is equal to 0 currents, which follow delta S is equal to 1 rule, where I is the isospin of the hadrons. This is what we have discussed in the previous lectures. Now, what happened? Gelman and Levy and Cabibbo proposed that the strength of the delta S is equal to 1 weak current. That means where K minus is decaying into mu minus nu mu bar, or lambda is decaying into proton, or sigma is decaying into neutron and E minus, and all that is suppressed as compared to delta is equal to 0 currents by a factor described by a parameter to be determined experimentally for the decays of strange mesons and baryons. See, this is what we call in physics as phenomenology, that we are proposing something and the parameters of the model would be determined by the experiments. It is somewhat similar if you recall Weizsäcker mass formula. Then in that case, the mass that you write, not only you write in terms of the proton, number of protons and number of neutrons, and multiplied by the mass of the proton and mass of the neutron, there you also take into account the Coulomb energy term, you take into account the surface energy term, you take into account the asymmetry term, and those coefficients are determined via the experiments. Therefore, that is a phenomenology. You are writing something based on the experimental inputs. Here also, the hypothesis we are talking about, we are saying that if you have involvement of first generation of quarks, that is U with S or S with U bar with S bar or S bar with U bar, that involvement will be suppressed in comparison to the involvement where U is interacting with D or U bar is interacting with D bar, or D is giving rise to a W minus and getting converted into a U and all that. Therefore, this is an important catch, that when you are talking about mixing of U with S, this we are saying that this is of suppressed strength in comparison to the mixing of U with D. And this in literature we know by the name Cabibbo hypothesis. Therefore, what is the hypothesis? The hypothesis tells you that actually this UD vortex, which initially we wrote it GUD and anticipated that this will be GW like in the leptonic sector, or same will be, you can write for muon. This which initially assumed, this in this hypothesis what is being told to us, that actually this is not GW, this is GW cosine theta c, a suppressed factor slightly than GW, because this theta c we will determine in the experiments. And if there is an involvement of U with S with a W, then this will be GUS and that will be GW sine theta c. Therefore, when we are talking about the matrix at the matrix element level, we have to consider GW cos theta c if we have the change of U to D, and we have GW sine theta c if we have the conversion of U with S or S with U, or U with U bar with S bar or S bar with U bar, such that if you see that when we are talking about K minus decaying into mu minus nu mu bar upon pi minus decaying into mu minus plus nu mu bar, then this is strength GUS square from the this is at the level of matrix element, and then we have the matrix element square, the actual quantity using which we will determine the cross section or decay rate. Then in the numerator we have GUS square, and in the denominator we have GUD square, and that is why this will be GW square sine square theta c upon GW square cosine square theta c, and that will be equal to tan square theta c. Now the important catch is, if we are determining this theta c to match the experimental result of 1/5 separation, and that we obtain it to be 13.0 degree, then we call actually this theta c as the Cabibbo mixing angle, or Cabibbo, simply Cabibbo angle. And if this is true, then this should be true for K plus upon pi plus. This should be true for lambda decay upon the neutron decay, or this should be true for sigma minus decay to neutron decay. That means decays where there is an involvement of U to S or S to U, or U bar to S bar or S bar to U bar, upon where there is involvement of U to D or D to U or U bar to D bar or D bar to U bar. This decay rate or cross section, this should be proportional to tan square theta c. Now what was done? First, looking at the few experimental numbers, phenomenologically it was found that with 13.1 degree we will be able to explain the experimental data. Now if this is really true, if this hypothesis is really true, then when we are taking this to obtain the ratio of lambda decay upon neutron decay, or when we are talking about sigma minus decay upon neutron decay, the decay channels which we have discussed in the previous slides, or k plus dk upon pi plus dk, then with the same parameter, it should explain the experimentally observed data. And really it was found that we are able to explain the experimental data if we assume that the coupling of u with d or u with s are of different strength, number one, and this strength for u with d is also smaller in magnitude in comparison to the first generation of leptons involving W exchange, or second generation of leptons involving W exchange. Let us stop here, and in the next lecture we shall talk about this Cabibbo hypothesis, and also we will introduce to Jim mechanism. Thank you very much.